You can just close that one. And can I make sure your mic's switched on?
Oh, yeah.
Oh, yeah, it is. Thank you. All right.
Great. We're super excited to welcome our next speaker, Amanda Coston. Amanda Coston is an assistant professor in the Department of Statistics at UC Berkeley. Her work considers a lot of important questions around machine learning and causal inference in societally relevant settings. She's won many exciting paper awards and many various distinctions. So without further ado, please we're all excited to hear from Amanda.
Thank you. Thank you for that introduction, and thanks to the organizers for organizing this awesome workshop. I'm excited to chat with you all today about the challenge of doing evaluations that are valid for algorithmic decision-making, predictive algorithms used to inform decision-making. And just use this. Okay, so I think perhaps the easiest way to kind of motivate some of these challenges is to compare the challenges we get in the algorithmic decision-making context against what we would encounter if we were just doing standard machine learning evaluation. Right, okay, so we all probably know the standard machine learning evaluation basics are that if we have some kind of data, and as long as we made sure to randomly partition it into a train and test sample, then it's pretty easy to evaluate a model. We just compare our predictions on the test set, and that gives us a good estimate of the model's performance. But we've seen a lot of examples, I think as most people in this audience are well aware, where algorithms that went through this process and then were then deployed to decision-making contexts in societally high-stakes decisions, like in human services or medical context, that these algorithms then proved to be problematic, exhibiting unintended behavior, making systematic errors that often exacerbated biases. And there's a lot to unpack in all of these examples. But in many of these cases, it seemed that this behavior took the algorithm developers and the people who were responsible for these deployment decisions, that it took them by surprise. Right? So the question is, why were they surprised by the behavior of these algorithms in the wild? And how did evaluations fail them? So what I'm going to argue is that evaluating decision-making algorithms is fundamentally much harder than standard prediction, and we need to really be careful to address these problems when we're doing evaluations if we want them to reflect what's going to happen in real-world settings. And so we can dive into this by considering more specifically a setting where we might be using an algorithm to inform decision making. And we'll see that this is one of the themes, that it's really important to think about the specifics of the context, to do this problem formulation step carefully in order to identify these evaluation challenges so that we can address them. The example that I'll walk through and kind of touch on throughout today's talk is, suppose we want to build a model to predict pneumonia risk for hospital patients. This comes from a decades-old paper by Rich Caruana and co-authors. And why do we want to do this? We want to do this because this will be used to inform who is going to be admitted to the ICU. Patients at high risk are going to be admitted to the ICU. If we think they're low risk, maybe we feel fine just admitting them to the hospital, not to the ICU. And why do we admit them to the ICU? Because we think that they're going to get better care there, and hopefully that will reduce their pneumonia risk. Right? So that points to the fact that whether the patient gets pneumonia or not can depend on that decision. And so we can see, we could imagine that there's a high-risk patient here. So this patient has, some risk factors like asthma, and they were admitted to the ICU. So this decision column here shows the historical decisions, and then we observed a good outcome. They didn't develop pneumonia. But we could imagine that counterfactually, had the patient not been admitted to the ICU, that they might have not gotten the right care, and it's possible they could have gotten pneumonia. So the key here is that we really don't want to just predict these historical pneumonia decisions, but we want to know what's going to happen if we don't admit patients to the hospital. And this is really important because, as they show in this paper, failure to think about this properly would actually cause you to build and think a model was doing well that would systematically screen people who had asthma as being low risk. So this is really bad because it's saying the people who are high risk and most responsive to treatment are going to do well under the proposed decision are actually the ones that you would be screening out and providing improper care. So what can we do about this? This really suggests that we should be thinking about outcome as not just one variable, this observed outcome that we observe, but rather there are multiple possible outcomes, there are potential outcomes. And if we have a binary decision like here, admitting to the ICU or not, then we're going to have two potential outcomes we can think about what would happen if they were admitted versus if they weren't. And which one of these we are interested in will depend on the setting. So to connect this back to the previous talk, my focus here is going to be on what Jan called the predictive targeting. We're going to assume that one of these is decision relevant. So in this setting, I'm making the argument that they want to make decisions based on pneumonia risk if not admitted. So we're going to say that this is our target of prediction. And of course, the challenge is that we only observe the outcome Y, which means that that outcome we really want to predict is only partially observed. We're only going to see these outcomes for people who got the decision the hypothetical decision that we want to predict outcomes under. Okay, so this is the first challenge, and I'm going to refer to this as the selective labels problem because this, or decision dependencies. So we're seeing that the outcome is dependent on decisions, and that we only selectively observe those based on their historical decisions. There are a lot of nuances for problems of this sort, and I'm just mentioning that we go into that in a paper here from 2023 led by Luke, who's over here in the audience. And then I want to go back to our data to introduce the second evaluation problem that we're also going to think about today, which is that I've introduced another column here on the right, which distinguishes the patient's actual health condition from the observed diagnosis, which is actually what Y represents. So this is a proxy outcome problem that's really common in a lot of settings, particularly in human services, but is also relevant to medical settings because we don't actually have ground truth outcomes on a patient's health conditions, but instead we're relying on things like doctors' diagnoses, and particularly for patients who maybe, in this example, they're not in the ICU, they're not getting as intensive care. It's possible that the doctors could make mistakes and they could have a health condition like pneumonia that goes undiagnosed. So in the data, they look low risk, but in reality, they are at risk, and it's just a failure of our ability to measure the outcome that we really care about. So here we're distinguishing this Y star of 0 as this is really the outcome that we care about, but we don't observe this. We're relying just on a proxy outcome. Okay, so now this picture is getting a lot more complicated. We're seeing we have missingness in some of the outcomes, Y0. We have this whole new outcome that's totally missing, which is really what we want to compare against. And I'm calling this the proxy outcome and measurement error problem. So we're only observing proxies for the intended outcome. And then I'm going to introduce a third problem to the mix. And so in addition to having some rows that may have partial or full missingness, some columns that may have partial or full missingness, it also may be relevant to our setting to think about rows that are missing. So for instance, perhaps the reason we're going through all this trouble is that we want to build this algorithm to deploy it at a new hospital. Let's say it's a rural hospital, but we only have data from an urban hospital, like somewhere in New York City. So we might ideally hope to have data on this rural hospital that we would use for this exercise, but instead we have to rely on this other data set, and that can really matter because patients at different hospitals can have really different demographics. They can have different incidences of risk factors like asthma that may be more common in one versus the other context. So putting these all together, these are the three common challenges that I'm going to focus on today that make evaluation really challenging in the decision-making context. That we have the selective labels and decision dependencies, that we only selectively observe outcomes under historical decisions, proxy outcome and measurement error, that often even that observed outcome isn't really the one we care about, but just a proxy for the one we do care about. And third, that we have distribution shift and selection biases, that we often are observing a different population that maybe we can approximate as a bias sample of our target population. I'll just pause here, see if there are any questions. And generally, please feel free to jump in with questions throughout. Okay, so we've been talking about these three problems that arise in algorithmic decision making. And next, I'm going to discuss about how this impacts evaluations and connects to core concepts in validity, and then we'll discuss some recent work on developing statistical methodologies to address these in practice, where we're going to draw on some commonly used techniques in causal inference. Okay, so valid evaluations. So when I talk about valid evaluations, I mean that the evaluation should be assessing the intended quantity, or more formally, we can ask, is the evaluation doing what it's supposed to do? In this paper from SAD-ML a few years ago, we go into the concept of validity throughout the algorithmic development pipeline, focusing on questions at problem formulation and development. Today's talk, I'm just going to focus on what this means for evaluations. And I'm going to introduce a few core validity concepts that will be useful. So construct validity, you may be aware of this from social science theory. This is asking to what extent the measure captures the intended concept. And then in our decision-making setting, this is asking to what extent our evaluation assesses the intended quantity. And we'll see how these problems that we've been talking about often threaten the validity of the construct. Another core validity concept concerns external validity. So in social sciences, this is classically to what extent the claims you're making in a study hold in real-world settings. And for our setting, this refers to what extent the performance metrics from our evaluation reflect how well the algorithm is going to perform in real-world settings. Okay. So the selective labels and decision dependencies problem we talked about, where we only observe outcomes under historical decisions, this can pose severe threats to construct validity, right? Because these observed outcomes are not valid to evaluate against when we have decision dependencies that cause intervention effects. We saw, for instance, the pneumonia example that it might, if you had an algorithm that's systematically screening out people who would benefit from care, an evaluation might still suggest, oh, that's actually a good algorithm, when in fact it's not. And so this has a lot of implications for if we're using evaluations to do model selection. It risks choosing a less performant or less equitable model than the optimal one, or greenlighting a model to be deployed when it really shouldn't be. This problem also threatens external validity, and I say that because this is a little more nuanced, but oftentimes in settings where selective labels arise, and people start thinking about this a little bit, or maybe it's even more natural because we only observe the outcome under one decision. So an example where that arises is in lending, where we only observe repayment outcomes if the applicant actually got a loan. So there it's common to just kind of not worry too much about the problem, because you're just going to focus on the sample where you observe the outcomes. But that poses risks for external validity, because typically that sample is just a biased sample of the target population that could differ in important ways. And again, that could lead us to choose a less performant or inequitable model, or greenlight a model that we really don't want to. Okay, so now on to our second problem area, proxy outcomes and measurement error. This problem also threatens construct validity, because the observed outcome is only an imperfect proxy for the target outcome. And there's an interesting body of work that shows how in practice this can render a lot of evaluation claims, including fairness analyses, quite fragile, that it's possible to get the observed conclusions or trends to reverse under plausible variations in the underlying measurement error. And so again, this is the same kind of problems that we've been talking about, that you may have some bar for fairness or accuracy that you want to pass, and if you're not accounting for all the uncertainty in your measurement error, you might feel confident deploying a model when really there's a lot more going on there. And then our third problem area, distribution shift and selection bias, I would argue is mostly around threatening external validity, because the problem is that the data set is not representative of the target population. And this means that there could be a model that is better on one population versus another. And if we're not accounting for these differences, we could again make the wrong decision about the right model to deploy, or whether we should even deploy a model at all. An interesting setting where there's a lot of discussion related to concepts around this is in clinical decision instruments. So a lot of clinical decision instruments have been developed using a cohort that's overly white and male relative to the populations that they're deployed on. And this leaves a lot of doctors and practitioners wondering whether they should actually be using these decision instruments to make treatment decisions for their patients, because they want to know, how well do these actually work on their patient population. Okay, so now I'll get into some of our work around how we can address these validity challenges in practice. And one of the themes we're going to see is this tension between, we're going to try to make as flexible assumptions as we can, but there's often a tension between that and actually being able to say something informative about the evaluation metrics. The work I'm presenting here today is joint with Esne, who's also in the audience, and Annie might be around here somewhere too. So if you see them, definitely chat with them. So prior work in this area, each of these problem areas has a really interesting prior work area that is worth diving into. There's a lot of work on imputation, counterfactual modeling, using doubly robust estimation to address selective labels and decision dependencies. A lot of work also on the measurement error and proxy outcome that uses measurement error modeling and sensitivity analysis frameworks. And on distribution shift, focusing here on a type of distribution shift called covariate shift. There's a lot of work on importance weighting and doubly robust estimation. But perhaps most relevant to our context, these methods are really focused on addressing each of these problems in isolation, whereas we're interested in these settings where these co-occur and what we can do to address the methods simultaneously. So we're going to start by jointly addressing two of these problems. This is work with Esne. So here we're going to say we're interested in the decision dependencies and the measurement error problem, and how can we go about doing valid evaluations that will address these two problems. So for now, we're not worrying about the distribution shift problem, but we'll come back to that if we have time. Okay, so I'm just going to introduce a little bit of notation so that we can discuss what's going on, and then we'll see some results. We've been talking about this idea of a target potential outcome. So in the example before, this is whether the patient has pneumonia under the decision relevant decision. Then we also have a proxy potential outcome that's partially observed. And then we can relate that to the observed outcome y through this equation that's making an assumption about consistency, that there's some subtle causal inference assumptions going on there, but we're just going to say we observe this proxy outcome. That's the outcome we would observe under treatment if the unit was treated, and it's the outcome we would observe under no treatment if, in fact, that unit was not treated in the decision, in the historical data. Then we have the decision D, features X, and we have some model Y hat that we want to evaluate. And our goal is to evaluate that against Y star 0. Okay, so the first step is the problem formulation piece here. What are our evaluation estimands? So we define these counterfactual measurement-aware versions of common predictive performance metrics. Here we're focusing on false positive rate and false negative rate. So these look like the standard false positive rate and false negative rate equations, except instead of conditioning on y, we're conditioning on this unobservable target potential outcome. So these are hypothetical quantities, right? These aren't actually things that we can observe or estimate in the data. If we want to have any idea of what this is, we need to make some assumptions that will allow us to connect these to connect these to things we can observe in the data. So the first assumption we're going to make is around what's going on in terms of measurement error. And we're going to make this a one-sided measurement error assumption. So this is saying, so measurement error we can think about having flips, like the observed outcome has been flipped from our target outcome in settings here where we're concerned with binary outcomes. And this one-sided measurement error is just saying those flips can only happen in one direction. So this assumption has been used in prior work that was motivated by the criminal justice setting. But in our setting, this is assuming that pneumonia may go undetected, but we're going to assume that it's not falsely detected. Of course, that is an assumption that probably doesn't hold in practice, but we're going to make that just so that we can make some progress here. And the reason that that's useful is that then we can describe measurement error using just this noise parameter that's describing the joint probability of the the target, the unobservable potential outcome equaling 1, and the proxy potential outcome equaling 0. Okay. And so that's halfway there to the identification. We've done the measurement modeling piece, but now we will introduce some causal assumptions. So these are versions of the standard causal assumptions. The first one, we're going to assume that treatment assignment is as good as random, conditional on our observable features X. And then we're going to assume positivity, that there is some level of randomness in our decisions. So it's not the case that there are certain covariate strata that would always be treated or that would never be treated. And then this consistency assumption I already mentioned before. So with these assumptions and that measurement error model on the previous slide, we can partially identify our performance metric estimates. So we can get these lower and upper bounds on our false positive and false negative rate. So where I'm using this notation, P's with a lot of sub and superscripts that are just describing joint probabilities between the outcome label taking a particular value and the proxy potential outcome identified under our assumptions as taking a particular value. So this is a counterfactual version of a result in prior work. Perhaps it's relevant to mention why we're getting partial identification here. So could we identify these estimates under our assumptions? And from our research and as well as in the kind of non-counterfactual setting previously, that seems like a really hard thing to do because in order to do that, you'd have to specify this additional measurement error parameter that depends on the joint probability with your predicted labels. And that's kind of a really hard quantity to think about. So that's why we get these bounds here. So that's going to be what we're interested in proceeding with are these bounds because these are things that we can theoretically compute in practice as long as we're willing to put some assumptions around the value of this parameter eta. Okay, so yeah.
How would you go about doing that? Like setting some bounds on eta?
I think it's a good question, and I think that would be an interesting, kind of empirical practice to find some real-world settings where this would be relevant and go through the exercise of talking with practitioners. Like, is this something that they can reason about? Is there related literature that has maybe looked at, has done some studies that would give us some sense of what this parameter might be? So I think those are the best kind of approaches. You either want to use some kind of domain knowledge, some auxiliary data analysis that would kind of suggest what that parameter would be, or maybe rely on experts who at least have some indication that probably this doesn't take a value beyond this amount or something. Yeah, it's a good question and an important one. So then once we've done the identification piece, then all that remains is how we're going to estimate that performance estimate. So we'll have a couple nuisance functions. These are just things that we need for estimation, although we don't directly care about them. So pi, the treatment assignment propensity, and the regression function mu. And so we're going to have the first step of our approach is going to be learning models of both of those nuisance functions, and then we can do some doubly robust estimation to estimate these bounds, these lower and upper bounds on our performance metrics. And the reason we do this doubly robust estimation is because this gets us nice properties. If you're familiar with doubly robust estimators, they're advantageous, for instance, in settings like what we're doing, where we're using flexible machine learning models. They have faster rates of convergence, better theoretical properties than if we just did something like what you might think of more simple, like doing some kind of simple regression plug-in procedure. So, okay, so now we can see a little bit about how this method performs and go back to this point that I was making about why it's really important to address these methods simultaneously. Whereas, with prior work, you would have had to choose which method you thought was most problematic for your setting and just go after an evaluation method that addressed that one. So here we do some synthetic validation of the method. And in these plots, we're showing false positive rate on the left panel shows false positive rate on the y-axis, and the right panel shows false negative rate on the y-axis. And then we're varying that measurement error parameter eta on the x-axis. And the red dot shows the oracle, so the ground truth counterfactual performance metric for false positive rate, for false negative rate. And we can see that if we did, naive, sorry, excuse me. So our method is this blue curve, and its bounds will include the ground truth parameter if we kind of specify eta accordingly. So going back to the earlier question, if we only considered it in a small window around 0, we would miss this. But hopefully we might have enough knowledge of the domain to know that we need a larger window on eta, and then our performance bounds would actually cover the ground truth. Whereas if we did one of the methods that only address one of these in isolation, it's not going to cover the ground truth. 4 minutes, yeah. Okay, so then I'm just going to kind of give the high level over the second part of our work, where we are doing something similar, except we're addressing the distribution shift problem and the decision dependencies. So here we're pausing on the measurement error problem and focusing, so we're not jointly addressing all 3 of these problems. I think that would be interesting for future work. But we do have a method here targeting this evaluation problem under covariate shift, while simultaneously addressing these decision dependencies. I'm just going to quickly go through this. Let's see. Okay, so our performance estimand is a little bit different in this setting, just for some variety. So typically performance estimands were either evaluating something on the full population, or as we saw in the previous section, on some class conditional population. So here we're taking these full population estimands like mean squared error. And again, we make the causal assumptions. And in this setting, we also introduce some covariate shift assumptions that restrict the what's going on with the distribution shift, so that we can actually make some progress in identifying our estimands. And so then we can identify this target risk estimand in terms of quantities in the data. And we do the same exercise as what we saw in the other setting. We're coming up with a doubly robust or double machine learning style estimator that has nice theoretical properties. We constructed this one from the efficient influence function. And then we have some results looking at this on hospital data, where the exercises that we've trained a model on a particular hospital, and then we're going to look at how it performs on a hospital with pretty different demographics. So the punchline is that we see some cases where failing to address, in particular for this data set, it looks like covariate shift is really important. So failing to address that risk, mistakenly deploying a poor model, or depending on the context, it could also mean you're overestimating your risk. And so that would mean the potential concern there is that you actually might want to deploy a model, but because your performance evaluation, you're overestimating risk, and you might think it's actually not the right model to deploy. So we find that those results can go either way. Failing to address these problems could lead you to both over or underestimate the risk of the model. We do some robustness of what happens when these conditions are violated, but I'm going to skip that for now and just wrap up. So we talked about validity. Does the evaluation assess what it's supposed to? Looking at these 3 types of threats and discussing some evaluation methodologies that use doubly robust estimation to address jointly 2 of these problems. So yeah, thank you all so much for your attention and just acknowledging some co-authors on the work. Yeah. Thank you.
The last bit of work, it seemed that part of what you're trying to do there is think about limits on transfer learning, right? And think about the model. And I'm wondering if you could talk more broadly about what kinds of shifts you can look at. Like you were talking, I think, about population distribution shifts. And I'm thinking about the medical setting where, for example, the shifts could be produced about like the timing of when measurements are taken or other sorts of things. I'm just wondering like what sort of work you're exploring.
Yeah, that's a great question. Yeah, I really went through that. I didn't get into the details. So in that work, we're assuming it's a covariate shift setting. So where the risk functions, like the probability of the outcome given risk features, those are the same across the distributions, but it's just the covariate distributions that could change. So that motivation about like maybe asthma is more common in one hospital area versus another. But so the setting where you're talking about where it's like, you were saying like how they kind of use instruments could differ from one versus the other. Yeah, and I guess that might be more of call into question that assumption on the risk model, right? That like, yeah, because if you're measuring like, let's see.
So you're thinking like disease prevalence, population, like those are the kinds of covariate shifts that you're looking at.
Right. So yeah. So the features that we measured that we're thinking of as X, so these could be like demographics, like race, age, or prior medical condition. Those we're thinking that those could vary from one place to the other. But it sounds like what you're saying is almost like what the feature represents varies from one to the other.
Yeah, that the organizational practices mean the same data has different meaning because of, things about when things were measured or calibration or like there's a whole range of things.
Yeah. That seemed, like an important problem and pretty complicated. I think that would most likely violate our assumption. I'm thinking because it would probably mean in that setting that like the relationship between those features and the outcome is different, and that would violate, that was one of the core assumptions. There is some work on label shift. It's pretty hard, like you need to make kind of some strong assumptions on what's going on there in order to make progress, but I think that's, an important problem. I'd be interested in chatting more if that's like an area that you kind of think a lot about it, yeah.
We're going to continue discussions offline. Okay.